Okay, so we are returning with regulation of blood pressure. Blood pressure regulation relies on the heart, blood vessels, and kidneys, which are all controlled by the brain. Three main factors regulating blood pressure are cardio output, peripheral resistance, and blood volume. Blood pressure varies directly with the cardiac output, peripheral resistance, and the blood volume. All right, so remember that F is the change in P over R. And F equals CO, or the cardiac output. So if we substitute for F, cardiac output equals the change in pressure over resistance. And if we rearrange this, we get the change of pressure equals cardiac output multiplied by the resistance. This shows that blood pressure, or MAP, is directly proportional to cardiac output and peripheral resistance. So changes in one variable are quickly compensated for by changes in the others. Recall that cardiac output is stroke volume multiplied by heart rate. So if MAP is cardiac output multiplied by resistance, then MAP is also equal to stroke volume by heart rate multiplied by resistance. Stroke volume is affected by the end diastolic volume, and are also known as the venous return. Heart rate is maintained by the medullary centers, and resistance is affected mostly by the vessel diameter. Blood pressure can be affected by neural and hormonal controls, which are short-term regulation, and also by renal controls, which are long-term regulation. Figure 19.9 is a nice graphic showing the effects of blood pressure, and particularly what increases MAP. So we have MAP down here. Increased stroke volume and heart rate increase our cardiac output, and increased cardiac output increases our MAP. Decreased blood vessel diameter, increased blood viscosity, and increased blood vessel length all increase our peripheral resistance, which also increase MAP. Okay, for short-term control, I mentioned neural controls. The two main neural mechanisms that control resistance are as follows. The MAP is maintained by altering diameter, which also alters resistance. So if blood volume drops, all vessels constrict, except for in the heart and brain. Secondly, the brain can alter where the blood is distributed based on the body's specific demands. Neural controls operate via reflex arcs that involve the cardiovascular center in the medulla, baroreceptors, chemoreceptors, and higher brain centers. Beginning with the cardiovascular center, it's composed of clusters of sympathetic neurons in the medulla. It consists of the cardiac centers, the cardio-inhibitory and acceleratory centers, and the vasomotor center, which sends steady impulses via sympathetic efferent vasomotor fibers to the blood vessels. This causes continuous moderate constriction called vasomotor tone. The cardiovascular center receives inputs from baroreceptors, chemoreceptors, and higher brain centers. Another neural control is the baroreceptor reflex. These are located in the carotid sinuses, the aortic arch, and the walls of large arteries in the neck and thorax. If MAP is high, increased blood pressure stimulates the baroreceptors to increase input to the vasomotor center. It also inhibits the vasomotor and cardio-accelerator centers, stimulating the cardio-inhibitory center, all resulting in a decreased blood pressure. The resulting decreased blood pressure is due to two mechanisms. The first is dilation due to decreased output from the vasomotor center. Blood vessels only respond to sympathetic innervation. Oops, let's just start this. Okay. They either constrict due to sympathetic innervation or dilate due to the inhibition of the sympathetic nervous system. Vasodilation of the arterioles results or reduces peripheral resistance, and the MAP falls. Venodilation shifts blood to the venous reservoirs, decreases venous return, and cardiac output. The other method used by the baroreceptors to decrease blood pressure is decreasing the cardiac output. Impulses to the cardiac center inhibit sympathetic activity and stimulate the parasympathetic. This reduces heart rate and contractility, and cardiac output decreases, so the MAP also decreases. If MAP is low, reflex vasoconstriction is initiated, which increases cardiac output and blood pressure. For example, a person stands up and blood pressure falls. This triggers the carotid sinus reflex, which ensures enough blood reaches the brain, and also the aortic reflex, which ensures the blood pressure in the systemic circuit. Baroreceptors are ineffective if the blood pressure changes are sustained. This is because baroreceptors adapt to the hypertension, and the elevated blood pressure doesn't trigger them anymore. Figure 19.10 in your text shows the baroreceptor reflex that helps maintain blood pressure homeostasis. First, we see that there's a stimulate. We're going to start in the top part here. We see that there's a stimulus to increase blood pressure. So maybe it's an anxiety for a big exam. And that is increasing your blood pressure. Secondly, the baroreceptors in the carotid sinuses and the aortic arch are stimulated by this increase in blood pressure. Thirdly, the baroreceptors send impulses that stimulate the cardioinhibitory center and inhibit the cardioacceleratory center and inhibit the vasomotor center. The decrease in sympathetic impulses to the heart causes a decrease in heart rate, contractility, and cardio output. The inhibition of the vasomotor center causes vasodilation, causing a decrease in resistance. Lastly, the decrease in cardiac output and resistance return the blood pressure to a homeostatic range. Now let's look at the bottom half here. In this case, a stimulus causes the blood pressure to decrease. So let's say you stood up quickly. The baroreceptors in the cardiac sinuses and the aortic arch are inhibited. This decrease in the baroreceptor stimulus activates the cardioacceleratory center. It also inhibits the cardioinhibitory center and stimulates the vasomotor center. Okay. These changes causes increased sympathetic impulses to the heart, which cause increased heart rate, contractility, and cardiac output. Also, the vasomotor fibers stimulate vasoconstriction, causes an impact in resistance, which then raises the blood pressure to a homeostatic level. Okay. All right, the second way our bodies regulate blood pressure neurally is in a short-term solution are chemoreceptor reflexes. Chemoreceptors in the aortic arch and large neck arteries detect increases in cardiac CO2 or a drop in pH or oxygen. Chemoreceptors can increase blood pressure by signaling cardioacceleratory center to increase cardiac output and by signaling the vasomotor center to increase vasoconstriction. The last way our bodies regulate blood pressure neurally in a short-term situation is the influence of our higher brain centers. Reflexes regulating blood pressure are found in the medulla. The hypothalamus and cerebral cortex can modify arterial pressure via relays to the medulla. The hypothalamus also increases blood pressure during stress and mediates the redistribution of blood flow during exercise and body temperature changes. Other than neural controls, our body also has hormonal controls that regulate blood pressure in the short term. Hormones change peripheral resistance in the short term, or they can change blood volume to regulate blood pressure in the long term. Epinephrine and norepinephrine from the adrenals increase cardiac output and vasoconstriction, thus increasing blood pressure. Angiotensin II and ADH cause vasoconstriction. Atrial natriuretic peptide decreases blood pressure by antagonizing aldosterone, causing a decrease in blood volume. Table 19.2 found in your text outlines the effects of the select hormones on blood pressure. I'm not going to talk through this, but you can read this and study this on your own. So the different hormones are listed, how they affect blood pressure. Notice that ANP is the only one that decreases it, the variables that are affected, and where it happens. Long-term mechanisms for blood pressure control include the renal mechanisms. Baroreceptors adapt to chronic high or low blood pressure, so they're ineffective for long-term regulation. So the kidneys alter blood volume. The kidneys regulate arterial blood pressure by direct renal mechanism and by the indirect renal mechanism of the renin-angiotensinogen-aldosterone mechanism. The direct renal mechanism works by altering blood volume without the involvement of hormones. Increased blood pressure or blood volume cause more elimination of urine, which in turn reduces blood pressure because there's less volume. Decreased blood pressure or blood volume causes the kidneys to conserve water and the blood pressure rises. Figure 1911 shows the direct mechanism of renal control on the left right here. So decreased pressure, decreased filtration, decreased urine. So instead, if we have less urine being made, our blood volume is actually higher, and that increases our blood pressure. The indirect mechanism the kidney uses for long-term regulation of blood pressure is the renin-angiotensin-aldosterone mechanism. Decreased arterial blood pressure causes the release of renin by the kidneys. Renin causes angiotensinogen from the liver to convert to angiotensin I. Then angiotensin-converting enzyme, or ACE, especially from the lungs, converts angiotensin I to angiotensin II. Angiotensin II acts in 4 ways to stabilize arterial blood pressure and extracellular fluid volume. It stimulates aldosterone secretion. It causes ADH, the antidiuretic hormone, release from the posterior pituitary. It triggers hypothalamic thirst centers to drink more water, and it acts as a potent vasoconstrictor, directly increasing our blood pressure. The right side of figure 1911 shows the indirect renal control of blood pressure. Decreased arterial pressure inhibits the baroreceptors, which then in turn increase the sympathetic nervous system to cause renin to be released by the kidneys. It converts angiotensinogen into angiotensin I. ACE then converts angiotensin I to angiotensin II. Angiotensin II works in 4 different ways. The first, it causes the adrenal cortex to release aldosterone, which then increases sodium reabsorption. We know that wherever sodium goes, water follows, so there's an increase in water resorption. Right there. And the increased water absorption causes an increase in blood pressure and an increase in MAP. The second way is that angiotensin II increases ADH release from the posterior pituitary. That directly affects water reabsorption by the kidneys, increasing blood volume, and then increasing MAP. The third way is it increases the thirst via the hypothalamus. This increases our water intake, our blood volume, and our MAP. And lastly, angiotensin II is a vasoconstrictor, which increases peripheral resistance and blood pressure. So please keep in mind the goal of blood pressure regulation is to provide enough adequate tissue perfusions, but not so high the blood vessels are damaged. Lastly, figure 1912 is a great visual of what methods our bodies have in their arsenal to increase MAP. Make sure that you understand them. This concludes